Hello, everyone, and welcome to Derivatives of Trigonometric Functions. We're going to start by making the graph of y is equal to sine of x. So hopefully you remember that sine starts at 0, it ends its period at 0, and in the middle it's 0. At pi halves it goes up to 1, and at 3 pi halves it goes down to -1. It's an odd function, so I can use that symmetry to graph the other side real quickly. And there's your graph of sine. So what I want to look at today is the slope of sine everywhere along its curve, because that's what derivative is. Derivative is slope. I'm trying to move this there. So when we look at the slope at 0, we could say it has a slope of, I don't know, let's say maybe 1. And if I say that, then just to be consistent, I would have to say it has a slope of 1 at 2 pi and at -2 pi. Now, if I'd said 2, that would be fine, but I just need to give it a number. That would also mean that at -pi, I would have to call that -1 to give it the same number, but I can see that it's going in the opposite direction. So at pi, -1. I know some of you already know what I'm going to do. And then the easiest one to identify correctly is that right at pi halves, it has a slope of 0. And at 3 pi halves, the slope is 0. So what I'm doing is I'm making a graph of all the slopes. At -pi halves, the slope is 0. At -3 pi halves, the slope is 0. And I'm sure you already see it. What do I end up with? I end up with the graph of cosine. What does this mean? That means that if y is equal to sine of x, the derivative of sine is cosine. If you want to know the slope anywhere along the sine curve, you would plug that x value into the cosine equation. It's funky, I know. So if I say to you y is equal to sine of x, let's actually call it f of x is equal to sine of x. And then I say, what is f of pi halves? Well, sine of pi halves is 1. That's its value. But if I want to know the slope at pi halves, the slope at pi halves is 0. And how can I get that? By plugging 0 into the cosine equation. And cosine of 0 is 1. All right, if you didn't understand all the meaning behind it, this is really the fact that you need to know. The derivative of sine is cosine. So trig derivatives are separate from product rule, quotient rule, power rule. They have their own set of derivatives. So let's do some problems. So remember this notation. This means the derivative, the D is for derivative, the parentheses mean of, the derivative of sine of 2x is going to be cosine of 2x. But hopefully you're already kind of guessing ahead. How does it change with that 2x? Times the derivative of the inside. So remember that that's the angle. If I say sine of pi halves is equal to 1, not as good, right? 1/2 is equal to 1. Remember that this is where the angle goes, and this is where the ratio goes. So what is sine of pi fourths? It's the square root of 2 over 2. So just a little trig refresher here. That means that if you have an angle that is pi fourths or 45 degrees, that means the ratio of the opposite to the hypotenuse is square root of 2 over 2. So trig is a connection between the angles and the ratios of the sides. So this is always the angle. It's connected. You can never separate that 2x from that cosine. But when you do the derivative, you're always going to write the exact same thing. The derivative of sine of 2x is cosine of 2x. The angle will never change. And then you need to multiply by the derivative of the angle. So in this next one, y prime, this is the angle. So the derivative of sine is cosine of x to the fifth. But then you would have to multiply by 5x to the fourth. Now, it doesn't gain you very much, but I will say that a lot of times, most times honestly, people will write it in the front because I don't want you to accidentally change this to cosine of 4x. And I don't want you to accidentally change this to cosine of 5x to the ninth. So let's just move that 5x to the fourth out to the front. Now, I put number 2 and 3 together because I want to make sure you see the difference between them. In number 2, it's sine of x to the fifth. In number 3, this is actually sine of x, the quantity sine of x to the fifth power. Completely different problem. I'm just going to tell you right now, I put these two types of equations on your test, and I put them back to back to reinforce that they're different. My advice is to write it this way every single time. It's really the guaranteed way to get it correct. And now it's easy. Now you're going to use power rule. Y prime is just like you've been doing for a little while now. Bring down the 5, sine of x to the fourth, and then the derivative of the inside, which this time is the sine. So the derivative of sine is cosine. You really don't have to rewrite this. But if you were going to rewrite it, I would just write it with the 4 back where it belongs. It's a little less cluttered that way. But this is totally fine. You can stop there. All right, we got a next one here. Keep changing the symbol. Y, f of x. You should be able to go back and forth between them easily. Oh, we didn't learn cosine yet. Any guesses? So we can do this pretty easily by just looking at the graph. Cosine goes like this from 0 to 2 pi. At 0, what is the slope going to be? The slope is going to be 0, which is sine. And at pi is going to be 0, which if you go back and look at your trig graph is exactly what it is. But it doesn't work out quite as nicely as we want it to, because at pi halves, the slope is -1, but sine of pi halves is +1. So what does that mean? That means that if y is equal to cosine of x, the derivative is negative sine of x. So it doesn't work out. It doesn't work out perfectly. So f prime of x is going to be, remember, the angle never changes. It's going to stay sine of 3x. It's going to be negative. And you still have to take the derivative of the angle, times 3, which I always write out in front so that you don't have to worry about writing 9x by accident. So you don't have to figure these all out graphically. I am going to give you the list of rules. Here they are. They're written a little bit funny. So to write them simply, we would just say when y is equal to sine of x, y prime is equal to cosine of x. So if you want to write them simply in your appendix, that's fine. But I do want to explain what this notation means. So I'll just use number 2 as an example. I'm not going to do all of them. This means the derivative of cosine of u. So instead of calling it cosine of x, they're recognizing that this might be something else. This might be 2x or 3x plus 1 or the square root of x. It's not always going to be as simple as just x. How do you do it when it's like that? You do negative sine of the same thing. See how that whatever this is still the same thing. But then you multiply, I've been saying, by the derivative of the inside, which everybody across the country does. But technically it's du dx. That means you take the derivative of just the u. So that's what that notation means. Don't let it frighten you. It makes perfect sense. The derivative of cosine of u is negative sine of u, but then you had to take the derivative of the inside or the derivative of the angle. So derivative of the angle. So even though I do try and simplify things for you, I do need you to understand the fancier definitions, no, the correct mathematical definitions. So this would mean, number 5, would mean the derivative of cosine squared 3x. Now, let's be clear. I'm going to actually rewrite this as y is equal to cosine of 3x squared. If you ever see the square here, I would move it to the outside. It's the safest way to do this problem. So we're going to do what we learned before. Bring down the 2. Now it's cosine of 3x to the first power. And now I'm going to do the derivative of the inside. Now think about it. This whole thing is going to be the derivative of cosine 3x because that's the inside in this case. So some people need to do it off to the side as a separate problem. They need to actually call it u, just like it is in the original rules up there. U is equal to cosine of 3x. So du dx, the derivative of u with respect to x, is going to be negative sine of 3x times the derivative of the angle, 3. Why am I making such a big deal of this? Because most people forget this 3. Because there's 2 insides. First we brought down the 2, cosine of 3x to the first, and now we're doing times the derivative of the inside. But this inside is cosine of 3x, which is going to have its own inside. Some of you are like, ugh, I completely lost her on that one. Negative 6 cosine of 3x sine of 3x. That's the answer. Don't worry, we're doing this all lesson. We'll figure it out. All right, more bad news. This is not always how the answer is going to look. You might remember that we did an entire unit, literally weeks, on changing how trig functions looked. We would do them on the board. We would do these big, long proofs. So the problem is that you don't know how the answer is going to look, and it might not look the same way that you did it, but maybe they're equivalent. So you're going to have to go back and do proofs like you did in pre-calc to show if the answer is the same as what you got. Or if you're in AP, it's possible that this is your answer, but it's not one of the multiple choice answers that's listed. So then you're going to have to figure out which multiple choice answer matches. So the one rule that you should really make sure you remember is this one from trig. 2 sine of 2x is equal to 2 sine x cosine of x. This was a double angle law. And how do I use that here? It means that if I want to change something to, if I have a sine and a cosine, I can write it just as a sine with a double angle. So this is actually the equivalent of this little piece right here, right? I'm going to change to just sine of 6x. But I also need the 2 from it. See how you need the 2? So that's going to leave me with negative 3 sine of 6x. If you're in honors, just skip ahead. You don't have to be able to do this. But if you're in AP, you need to recognize that this and this answer are the exact same thing. They've applied the double angle law. They've used the 2, the cosine, and the sine to change it to just sine of 6x. And there's still a negative 3 left. It's very tricky. I always tell people the AP test is really practically like a whole high school test. It's going to check all your pre-calc, your algebra, everything. All right, number 6. Number 6 is easy. Y is equal to secant squared x. What was my point of doing that problem then? 2 things. Number 1, if you're in honors, you better make sure you have a good appendix. And if you're in AP, you better make sure you memorize all of these, because what you don't want to do is to have to change it to y is equal to sine of x over cosine of x and then use the quotient rule. Is it possible? Yeah, this is where it came from. This is how somebody figured out that it was secant squared x. Y prime would be the bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared, which became cosine squared x minus plus double negative sine squared x all over cosine squared x, which is 1. Remember that from trig. Cosine squared plus sine squared is 1 over cosine squared x, which is secant squared x. Much better to just memorize the rule, okay? So memorize that, or if you're in honors, write it down. But that's where that came from. So number 7 and 8 look like I made a mistake. I did not. I'm going to show you 2 different ways of doing the same thing. One is if you have your secant rule memorized, then use secant rule. But I cannot stress enough that your first step should still be to bring the square to the outside. And now your derivative will be 2 secant of 5x to the first power times the derivative of the inside. A lot of people don't do the inside correctly because they don't consider it its own problem. So if I were you, I would do it off to the side and say, this is the inside. I'm going to pretend this is my only problem. How would I do it? So the derivative of this is secant of the exact same angle times tangent of the exact same angle times the derivative of the inside, which is the angle. All of this is what needs to go there. So 5 secant of 5x, tangent of 5x. So your final answer is 10 secant squared 5x, tangent of 5x. This extra 5 right here, that's what people forget. All right, we're going to do this one a different way. Some people are like, you know what, I'm going to change it to cosine 1 over cosine squared 5x. And then, because it's a constant on top, we've talked a lot about this, bring it to the top. So cosine of 5x, and I still want you to bring the power to the outside. So I still haven't done a derivative. It's really important that you keep labeling your work. Y is equal to, y is equal to. Now I'm going to do y prime. Negative 2. This stays exactly the same. Don't take the derivative yet. Don't change it to sine yet. To the negative 3. Now times the derivative of the inside. If you think you're going to do it wrong, do it off to the side. U is cosine of 5x. The derivative of that is negative sine of 5x times 5. I keep doing it off to the side because this has its own inside. So when people take the derivative of the inside, they do it too quickly. They forget that there's another derivative of the inside. So this is negative 5 sine of 5x. So y prime is equal to 10 sine of 5x over cosine cubed 5x. Uh-oh. Do the answers match? So when you're doing your homework and you go to look at the answer in the back of the book, and you got the green answer and you see the blue answer, I don't want you to freak out and say, oh, I did it wrong, and start all over again. In trig, you always have to ask yourself, is this the same answer written differently? And if you're in AP, recognize that you might get the blue answer, but the multiple choice answer might be green, and you need to recognize that as the same answer. So how can I show you that it's the same answer? Really easily on the blue one. So I'm going to break that down into 10 sine of 5x over one of the cosines. That is not writing nicely. There we go. Cosine of 5x times 1 over the other two cosines of 5x. And that does give me 10 tangent of 5x. And then this becomes secant squared of 5x. So they are the same, but they don't look it. And this is really a sticky spot for kids in trig derivatives, that you're doing the problems right and you just don't know it because you don't see your answer there. Okay, number 9. Give that a little star. I put something similar on a test or a quiz, and most people get it wrong. They get it wrong because they're not willing to do it as 2 parts. When you have a problem with tangent, you have to say to yourself, this is y prime is equal to, the derivative of tangent is secant squared of the exact same thing times the derivative of the inside. You are going to be most successful if you're willing to do this separately. So just pretend it's a whole new problem. Forget that there's ever a tangent in there. If I just said to you on a quiz or a test, what is the derivative of the square root of 3x? You would change it to a power. Then you would use the power rule. U prime is 1/2 3x to the negative 1/2 times the derivative of the inside. I know that did not look too hard, but for some reason, when people try and do it as part of a bigger problem, they get it wrong. I know I've said it like 5 times. Somebody's still not listening to me. So this becomes 3 over 2 square roots of 3x. This square root of 3x is attached to the sign. It does not cancel with this one out here. So this, as a final answer, would be 3 secant squared square root of 3x over 2 square roots of 3x. And again, these square roots of 3x cannot be canceled. One is stuck with the sine squared. Very, very challenging problem, number 9. All right, if you want to stop the video and try number 10, you can, but I am going to do it for you. Hopefully you realized it's product rule, our first one with product rule and trig. We're starting to combine everything. The second times the derivative of the first plus the first times the derivative of the second. Product rule. You could write it like this if you want to, without the parentheses and everything, but it doesn't really buy you very much. I'll take the boxed answer. And now, quotient rule. They used U just to be tricky. U, Y, W, all the same. U prime is the bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared. u prime is, I'm going to simplify, I'm going to distribute that. So negative sine of x plus sine squared x plus cosine squared x all over 1 minus sine of x, the quantity squared. The sine and the cosine become 1. So now I have 1 minus sine of x over 1 minus sine of x squared. So this entire 1 minus sine of x cancels with one of the two. 1 minus sine of x is on the bottom. And that gives me 1 over, don't forget that 1 over. We still have things on the bottom here. 1 minus sine of x. If you tried it on your own and you got it right, good for you. So this one's asking for the second derivative. So the first derivative of secant is secant x tangent of x. It's just a rule. You literally look it up on the list, write it down. But to do the second derivative, don't forget its product rule. You can't just take the derivative of one trig function at a time. You have to use product rule. So the second times the derivative of the first, the derivative of secant is secant x tangent of x plus the first times the derivative of the second. The derivative of tangent is secant squared, giving me a final answer of secant x tangent squared x plus secant cubed x. Now, some people, which I love, might be thinking, oh, I bet if I factor out the secant, something good happens. It does. You'll get the tangent squared x plus the secant squared x. And at a glance, you might think that that's a 1, but it's not quite. The rule is 1 plus tangent squared x is equal to secant squared x. So unfortunately, to get 1, you need secant squared x minus tangent squared x. But if you were even thinking that something good was going to happen from factoring and getting 2 squares, that was still the right train of thought because that's going to happen in the future. But in this particular case, it doesn't help. Okay. So that's the end of the in-class examples. I cannot stress enough that this is going to be a challenging homework. When I used to tutor calculus, this was literally when 50% of my calculus kids called up and said they needed a tutor, was during trig functions. They're very challenging. So make sure you do a lot of practice problems. All right, a little bit of theory. I'm going to, instead of teaching days and days of theory, I'm just going to throw in 5 minutes every once in a while. It's going to look unrelated, but I'd rather do it in small doses. Let's look at the graph of sine of x close to the origin. So sine looks like this. Remember, it's an odd function. So if I look at it close to the origin, meaning I just blow up this one little piece, the graph actually resembles a line. And the closer I get into it, it really, you wouldn't even know it was sine. That little piece right there just looks like a line. So let's find the equation for the line. Ooh, I love these. Find the equation of the line because they're always the same. Y is equal to m times x minus x1 plus y1. All you need to find the equation of a line are 2 things, slope and a point. Well, the point is easy. We know that sine passes through 0, 0. And we need to know the slope at 0. So Watch this. What is the slope of sine of x at x is equal to 0? Mathematicians thought of a mathematical notation that literally means this. That is f prime of 0 if f of x is sine of x. That is literally what that means. So if you have a function sine of x, this entire sentence, what is the slope of sine at x is equal to 0, can be summed up in that little notation, f prime at 0. So if f of x is sine of x, then f prime of x is cosine of x, and f prime at 0 is cosine of 0, which is 1. So my slope is 1. And it looks like 1, right? If you look at that slope, it looks like it's 1. So what is the equation of the line? Y is equal to x. That's the answer. So for values close to 0, the linear equation we found gives a good approximation of sine of x. So this is a very archaic concept, or very archaic use. The concept of it is really important. What it's saying is, I want to know sine of 0.12. This is ridiculous. You guys have a calculator. You would just plug it in. But as recently as my dad's generation, they didn't have a calculator. So if they wanted to know sine of 0.12, they would say, well, at 0, sine and y is equal to x pretty much look identical. So I'm just going to say that sine of 0.12 is 0.12, because right around the origin, it's pretty much just the line y is equal to x. Find sine of 0.12 with your calculator. So first, I do want to just check the mode real quick. I am in radian. For calculus, you never have to change it, unless unfortunately you're also in physics, then you're going to be going back and forth. But all year, every day, calculus is in radian mode. So if you only take calculus, you are good to go. So sine of 0.12 is pretty much 0.12. So it's a good approximation. I want to quick show it to you graphically. Y is equal to sine of x, and y is equal to x. When I hit graph, oh, I have mine on some kind of funky window from another class. Zoom 4 is a great window. So here comes my sine, and look at that. Do you see that y is equal to x and sine of x are pretty much the same graph right there? If you really want to look at it up close, from -1 to 1, and then the same thing here from -1 to 1. Really, that little tiny box that I was trying to show you on paper, there's your sine graph. Look at that. They're right on top of each other. We call that concept local linearity. So in a local spot, at a location, it's very linear. So there was your little bit of theory for the day. But trig derivatives, very tough. Good luck with them.